Welcome back to our OpenFOAM tutorial series. In this session, we will explore the offset cylinder case, a simulation that demonstrates how to set up a flow around an offset cylindrical geometry and analyze the results. The offset cylinder case is designed to study fluid behavior around a cylinder placed off-center in a domain. This creates asymmetrical flow patterns, making it ideal for learning about wake formation, vortex shedding, and pressure variations. Okay, so to study the offset cylinder, we need to go inside the OpenFOAM tutorial. Okay, so let's go inside OpenFOAM tutorials. Then I will go inside incompressible. Then I will go inside non-Newtonian icofoam, and then press ls, and here you will find this offset cylinder. Okay, so what I will do, I will just copy this one, copy offset cylinder to my home directory. Okay, so let us go to our home directory, and here we're having offset cylinder here, so let's go inside there. Okay, so we will go first inside the system, okay, to check the dictionaries. So only block mesh dict is there, these has to be there, so no need to there is no need of any command to run for them. Only block mesh is there, so we will run block mesh and then we will run the solution. Okay, we will run the solver command. Okay, so let's check the block mesh dict. Okay, so this is some new type of block mesh dict. Okay, it's not like the general one which you should see generally, or which I have shown you in the previous lessons. Okay, so let's go what this block mesh dict is about. Okay, so this is the header specifically. So this header specifies that this is a block mesh dict file which is used to generate the mesh. It includes OpenFOAM version details and file from format specification. So up to this I have gone through. Next is about the scale. So the scale entry is set to 1, meaning all dimensions are in meters. Additionally, we see Zmin and Zmax defined as -1 and +1 respectively. These control the 3D extrusion thickness of our mesh, since the geometry is essentially 2D but extruded in the Z directions. Okay. Now next is the vertices. So here you can see that beforehand only the Zmin and Zmax has been defined. Okay, so we don't need to define again and again -1, -1, -1, -1, -1, and here when the Z max is required, so there will be no need to define 1, 1, 1, 1, 1 again. Okay, so this is a very good practice. If there is a long OpenFOAM code of the block mesh dict for the making the mesh, and again you are going to use the Zmin. Okay, so you can just define here once and then you can use that. Okay, because x and y coordinates, these are changing. Okay, so you cannot define them here, but these are repeating around you can say that around to 15 to 20 lines, and again 15 to 20 lines this Z max is being repeated. Okay, so it will be wastage of time, and again there may be a chance that you may get inaccurate or you may get wrong. Okay, sometimes what happens is, like, in place of defining -1 you may define +1, and then when you run block mesh then you may get error. Okay, so this is a very good practice to define it like that and then use the naming which you have given here and use here in the coordinates. Okay, so the vertices section lists all corner points of the mesh. Each vertex has x, y, and z coordinates, with zmin and zmax defining the lower and upper planes of the domain. These vertices form the foundation of our mesh blocks. Alright. Okay. So let's go uh, to the blocks section. Okay. So here are our block section. You know why it is being used. These are being used to define the number of blocks. Okay, so here we see a series of hexahedral hex blocks created by connecting vertices. Each block specifies the vertices used, number of cells in x, y and z directions, and the grading, which here is set to simple grading 111 for uniform cell size. Okay, so this is about blocks. Okay, next is the edge section. Again, now here you can see that edge is being also defined like that, because y arc, you will see about that in the paraview, but here I will define here also. So in the edges section, we notice multiple arc entries. These are used to define curved edges for the cylinder instead of approximating it with straight lines. Each arc is defined between two vertices and an origin point, which in this case is 0, 0, z, ensuring a smooth circular profile. Okay, so this is about the edge section. Now here we come about the boundary. So here we are defining about the boundary, that which part is the left, which part is the right, which part is the down, which part is the up, and which part is the cylinder. Okay, so here we will be defining about boundary because this is very much required. Okay, so this is the boundary section, defines the physical boundaries of the simulation domain. Left and right patches are defined as patch type representing inlet or outlet. Up and down are walls. Cylinder represents the cylindrical obstacle in the flow and is also a wall boundary. Each boundary specifies its faces, which are groups of vertices forming surfaces. Okay, so my aim to choose this case as a tutorial, as an advanced tutorial, is to demonstrate you this type of blockmesh file. Okay, because there are many types of blockmesh file. Okay, so simply what you can do, like another way was like to define a rectangular domain with the general block mesh which we are using. Then with the help of snappy hex mesh, you put on a cylindrical hole. Okay, and then you just make the flow and check the pattern, how the pattern is moving. All right, but I am but here you don't need to go for the block mesh for the snappy hex mesh. Okay, because for the snappy hex mesh, you need to make the model of the cylindrical pipe in a 3D software. Then you need to save it. Okay, and then you need to bring up here in the OpenFOAM constant try surface, and then after running the block mesh, you have to run a snappy hex mesh. Okay, sorry. So why to go with that method when you can make with the whole mesh, the required mesh of yours, with the help of the block mesh. Okay, so that is the part. Okay, so once the file is ready, we run block mesh to generate the mesh. The resulting mesh captures the offset cylinder geometry with curved edges and uniform refinement, ensuring accurate CFD results. Alright, so this is about the block mesh dict. Let's go back. There is no other dict. Okay, if you wanted to see the control dict, we can go for that also. So we will go for control dict. Here we will find application non-Newtonian icofoam. Okay, and here start time 0, stop at end time, and time is 2 seconds, delta t 0.025, right interval 0.05. Okay, all these things are here. Right, so we will go back, and then we will just run block mesh, press enter. Okay, so our mesh has been made. Okay, so let's check our mesh. Okay, before running the solver, let's check our mesh. So for that I have to make .foam file, which I have made. Then I will go to paraview.exe foam.foam and press enter. Okay, here we are, and press apply. Go to wireframe, and here is our mesh. You can see how beautifully mesh has been made. Okay, what a perfect mesh it is. What a perfect mesh. Okay, what a perfect mesh it is. All right, you can see with this. Wow, no distortion, and like What a beautiful mesh. Okay, you can see that how the cylindrical profile has been made here. Okay, how the cylindrical profile, how the connection of the vertices has been made. Okay, see, you can see only with the help of the rectangular cells, all wherever you can find that all only rectangular cells are there, they are on the curve, but rectangular cells are only there. Okay, so that is, okay, that is basically, this is the block mesh file, the block mesh dict which we have made. So these are specifically made by the advanced OpenFOAM users. Okay, and the knowledge of this is very much required. All right, so this has been done. Okay, this has been done. All right, so now let's run the solver. I will close this, then I will just clear the terminal, and I will just type the name of the solver. Okay, I forgot, so to check again I will go inside control dict, and here is the name of the solver in front of the application, non-Newtonian icofoam. I'll copy this by pressing control C, go back again, right click, press enter. Okay, so it will take some time to complete. Okay, okay, so our simulation is complete. Now we will go to the para view to check about the results. So okay, so I'll press apply, and here we go. These are the results. Okay, so basically the flow is happening from left to right. Okay, if we will just go for the velocity, you can see that above the cylinder the velocity is higher. Okay, if I'll just move it, we'll just move it to the last second. So okay, I'll just play it. So you can see that the velocity is being increasing, but yeah, I mean, you know, it's not been quite visible here. So what we will do, we will try to check it via this one, the streamlines. Okay, so how to make the streamlines? We will go with the help of stream tracer, and I will type point cloud. I will choose point cloud here. Okay, so this is a point cloud. I will just move it a little bit here, and on the front side also. Because lines sometimes don't give the results in the way we want. Okay, I will just close this, and will, yes, you can see. Okay, the just a minute, just open this OpenFOAM, and I will just choose wireframe, yes, to visualize the results. Right, so this is the result, and here what I will do, I will just choose solid color. Okay, and then we will again go to stream tracer. Okay, here what I will do, I will just close the show sphere, and what we can do, we can, okay, yeah, I have decreased the streamline 7. Let me increase it up to 8. Press apply. Okay, number of points. Okay, let's increase the number of points up to 500. Yes, so here we are. Okay. So you can see that the how the flow is happening. Okay, how the flow is happening here. Okay, You wanted to see on the surface, you can choose the surface. Oh, you can choose the points also. Yeah, it is now more visible to you. All right, more visible to you. And one more thing we can do, there is one option of okay, here it is. Now what I will do something else also. Warp by vector. Let's apply. No, this is not the thing which I want. Okay, I mean with the stream tracer also you are all able to, you know, check, visualize it. Okay, like you know, how is the thing going on, how the flow is happening specifically. Okay. And that was my major major aim for this case. All right, for this case. Okay, so yes. So this concludes the offset cylinder tutorial. We have learned how to set up the case, run the simulation, and analyze the results. In the next lesson, we will explore more advanced techniques to study complex geometries and flow conditions.